Why do we require more effort to pull the door handle when it is near to the hinge? To understand this, we need to understand what torque is and what role it plays in the turning effect of forces. The door is a rigid body that is not deformed by the force or forces acting on it. In this rigid body, the turning effect occurs when all the particles of the body move angularly with their centers all lying on this line, which is called the axis of rotation of the body. Two factors determine the turning effect of the pull on the door. These are the magnitude of the pull, or the applied force, and the perpendicular distance of the pull from the hinge. In symbols, torque, also known as moment of force, equals F times D, where F equals force measured in Newton, and D equals perpendicular distance from hinge, measured in meter. This makes the SI unit of torque to be Newton meter, as both units are multiplied, also written as Nm. Torque is a vector quantity that depends on both magnitude and direction. Principle of torque. The principle of torque, also known as the principle of moment, states that when a body is in equilibrium, the sum of clockwise moments about a pivot is equal to the sum of anti-clockwise moments about the same pivot. For example, we commonly see in markets that a beam balance is placed with calibration weight at one end and your chosen fruits or vegetables at the other. For the equal arm beam balance, the distance d between each pan and the pivot is the same. Now, we let the unknown mass of the oranges we want to buy be m kilograms and want to find how many calibration weights needed to balance the beam. If 3 calibration weights, each of s kilograms, are required to balance the oranges, we conclude that the mass m of the oranges is 3s kilograms. Hence, from the principle of moments, the clockwise moment of the beam must be equal to the anti-clockwise moment. Using this, we can calculate the unknown mass of the oranges. Since weight is a force, by the principle of moments, the weight of the oranges times perpendicular distance from the pan of the oranges to pivot equals the weight of the calibration weights times perpendicular distance from the pan of calibration weights to pivot. In the original equation, force equals mass times acceleration, but weight may be defined as the force of the gravity on the object. So we can substitute the equivalent and get the torque formula become mass of the oranges times acceleration of gravity times perpendicular distance from the oranges to pivot, mgd, equals mass of the calibration weights times acceleration of gravity times perpendicular distance from the calibration weights to pivot. Substitute the mass of calibration weights with 3s. mgd equals 3s gd. Thus, when the equal arm beam is balanced, the mass m of the oranges is equal to the total mass of 3 calibration weights. m equals 3s. Conditions of equilibrium. When an object is stationary, all the forces acting on it cancel each other's effect, and thus resultant force is 0. Similarly, we just learned from the principle of moments that when an object does not rotate, the clockwise and anti-clockwise moments acting on it are balanced. Thus, an object in equilibrium will always have 0 resultant force and resultant moment acting on it.